Confidence intervals. In hypothesis testing, we have been using alpha as the probability of type 1 error, and the standard we have been used so far is 0.05. That is the probability of type 1 error. So if the probability of error is 0.05, the probability of having no error is what we call confidence level. So that is 1 minus alpha. So if it is 0.05, it should be 0.95. We used to do this null curve for our hypothesis testing centered around the mu, mean under the null. So what we do is we go on right side of this curve and left side of this curve for this two-tailed test, and we used to split alpha into equal halves. So this alpha used to be like 0.025 on this side, and the corresponding z value in the table is minus 1.96. Towards the right, alpha by 2, we can go and find it at probability value of 0.975, and the corresponding z value is 1.96. So z either on this side or on that side, the value is the same, except the sign is opposite. Positive on this side, negative on that side. So in a two-tailed test, our alpha is divided onto both sides, 2.5% on each side. So total alpha on this curve was given to us was 0.05 or 5%. And the middle part is our confidence, that is 95%. We have been using this equation for z, where we have this sample mean y bar and how far it is away from its population mean in terms of standard error scale. So here, if we want to calculate mean from this equation, we can rearrange the equation, and finally what we get, this thing, that is y bar mu is equal to y bar plus minus z sigma y bar. And since this z is correlated with the alpha, so we can plug in the alpha also in this equation. So the equation becomes y bar plus minus z alpha by 2 into sigma. Remember, confidence interval is always two-sided. So we have a lower confidence interval as well as the upper confidence interval. Confidence interval is where we gave two intervals, lower and upper, and then we define our confidence level. That is, we can do it by plugging in the relative value of the alpha. So if we plug in alpha of 5%, our confidence level is then 95%. So these intervals, lower and upper, they then give you that particular level of confidence about the population mean. So we can say that we are 95% confident that our population mean is between these two intervals. We calculate those intervals by using the sample means and adding and subtracting this part onto it. Generally, we have samples in our hands which are coming from the sampling distribution of the means, and that is coming from some population, and we want to estimate the properties related to a population or the parameters from using these statistics. Like this sample mean can be used to estimate the population mean, and same way sample standard deviation can be used to estimate the population standard deviation sigma. From central limit theorem, so far we know that if we have n sample size greater than or equal to 30, we can use S, or this sample standard deviation, to estimate the population standard deviation. And since we know sigma and since we know n, we can also calculate the standard error. Since we have the standard error and we also have the sample mean, and we do have alpha, and we can have the corresponding z value for that particular alpha and plug in into this equation. So in this way we can get a confidence interval for the mean like this. So the formal definition, confidence interval is equal to y bar plus minus z alpha by 2 into sigma y bar, which is the standard error. This part of the equation, this addition and subtraction which we are doing actually, is called margin of error or marginal error. Alpha is 0.05, so that is our probability of error. So how much confident we are? 95% confident. So in this case, it becomes a 95% confidence interval if alpha is 0.05.